Good morning, students. We are learning water resource engineering and hydrology. We are discussing about hydrological parameters. In the previous lecture, we have discussed on the factors that affect the infiltration rate, where in today's lecture, we will discuss about measurement of infiltration. How we can measure the infiltration. Infiltration capacity of a soil that can be measured in the field by conducting a controlled experiments on small areas by using infiltrometer. Well, we have two different types of infiltrometer. The first, that is flooding type infiltrometer, and the second one is rainfall simulator. Well, discuss about flooding type of infiltrometer. Well, this is a instrument wherein essentially there would be a metal cylinder of diameter having 25 to 30 centimeter and the length about 50 to 60 centimeter. It is open at both the ends. This cylinder is driven into the ground with a driving plate and a hammer such that it having about 10 centimeter length that projects above the ground surface. The top surface of the soil inside the ring is protected by a metallic dish cover. Okay, now after that water is poured into the top part of the depth about 5 centimeter, and there would be a pointer to be set to mark a particular water level. Well, as the infiltration takes place, the water level goes down and the water level will maintain constant by adding the water from the burette. Well, reading of the burette are also taken at a regular interval to determine the rate and the amount of infiltration. Well, the experiment is to be continued till a uniform rate of infiltration is obtained, and this maybe take 2 to 3 hours, that depending upon the type of soil and the moisture that available in that soil. Well, a graph to be plotted between the infiltration capacity and the time for the better understanding of the infiltration effect. Okay, so this is the first flooding type infiltrometer, that is a simple infiltrometer. Now also we have one more flooding type infiltrometer, and that is double ring infiltrometer. Well, this double ring infiltrometer is the most commonly used flooding type infiltrometer. It consists two concentric rings that driven into the soil uniformly without any tiltation, and without disturbing the soil to the least to a depth of 15 centimeter. The inner ring of this infiltrometer is usually should be 22.5 centimeter in dia, and outer ring should be having diameter of 35 centimeter. Well, the inner ring or the inner tube is used to determine the infiltration rate, as in the case of a simple infiltrometer. Well, the water is applied in both the inner and the outer ring to maintain the constant depth of 5 centimeter, and then water is replenished after the level falls about 1 centimeter. Well, the water depth in the inner and the outer rings that should be kept same during the observation. Thus, the outer ring that provides a sort of water jacket to the inner rings, and the water in the inner rings that infiltrates vertically downward without spreading surround. Well, the reading of volume of water that should be added at successive time intervals to maintain the constant depth of flooding in the inner ring to facilitate the computation of infiltration capacity or the infiltration rate. Well, this double ring infiltrometer is more accurate than the simple flooding type infiltrometer. But with all of that, there are several challenges that is related to using such kind of ring infiltrometers. Well, in double ring infiltrometer, the pounding of the infiltrometer into the ground deforms the soil, also compress it, or it also may cause the cracks which can affect the measured infiltration capacity. Well, this ring infiltrometer cannot reliably characterize the infiltration of furrow irrigation or the sprinkle irrigation or of any kind of rainfall. Well, with the single ring infiltrometer, the water spreads laterally as well as the vertically, and this analysis will become more difficult when this water will spread vertically as well as the laterally. So these are the problems that create while using the ring infiltrometers. Well, the next type of infiltrometer, that is the rainfall simulator. Well, in this type of infiltrometer, water is applied in the form of a spray as shown here with this with the help of this nozzle. Okay, now a plot of size about 4 to 4 meter by 2 meter should be selected, and on that a water is to be applied in the form of artificial rain at a uniform rate. Now, for applying the water, two rows of special type of nozzles are installed, one along with the each. Well, here the specially designed nozzle produce the rain drops that falling from a height of 2 meter and are capable of producing various intensities of rainfall. Well, various intensities of rainfall can be simulated by changing the nozzle openings. Well, experiments are conducted under a controlled condition with the various combinations of intensity and durations. And also the surface runoff is measured in each of the case. While using this water budget equation, that involving the volume of rainfall, infiltration and the runoff, the infiltration rate and its variation with the time are also calculated. So for such case, infiltration would be equal to the rainfall minus surface runoff. Okay, well, in this formula all the terms are expressed as the depth of the water over the plot, and the rate of infiltration can be determined from the total infiltration depth. Rainfall simulator type infiltrometer give the lower value than the flooding type infiltrometer. So this is due to the effect of the rainfall impact and the turbidity of the surface water, which generally decrease the permeability. So this was the rain simulator, and previously we have discussed about flooding type of infiltrometer. Now we will discuss about an equation to find out the infiltration capacity, and that is the Horton's equation of infiltration. Well, the maximum rate at which the soil in any given condition is capable of absorbing the water is generally called as the infiltration capacity that we have discussed about in previous lecture. Well, infiltration oftenly begins at a high rate of about 20 to 25 centimeter per hour and then decrease to a fairly steady state rate as the rain continues. And this process or this variation that is called as the ultimate infiltration capacity, or we can say the ultimate infiltration. Well, this Horton have developed a mathematical equation for finding the rate of infiltration capacity, and he has also developed a curve for the infiltration capacity at a particular time or at any time, we can say. Well, the equation, that is F is equals to Fc plus F0 minus Fc into e raised to minus kT. This is the Horton's equation to find out the infiltration capacity. Well, here F0 is the initial rate of infiltration capacity. Fc is the final constant rate of infiltration at the saturation point. And the K is a constant that, depending upon the soil and the vegetation, the value of this K is F0 minus Fc upon Fc. With that also, this is a graph that Hortons have developed for the infiltration rate. Well, here you can see the value of this K. Here at the y-axis there would be an infiltration rate, and at the x-axis with the variation of time we can find out this infiltration rate. Okay, that would be a constant value with the time wherein the infiltration would be constant. So let's solve this Horton's equation. First of all, Horton's equation is F is equals to Fc plus F0 minus Fc into e raised to minus kT. Now let's transpose the Fc value to the different side. So F minus Fc is equals to F0 minus Fc into e raised to minus kT. Now this value of e raised to minus kT, if we convert it into the log values, we need to take log at both the sides. So by conducting log both the sides, we will have log F minus Fc base 10 is equals to log F0 minus Fc base 10 minus, once log e raised to something will be come at front side, so that's why this kT at the front side. So kT log e base 10. Well, now make t as a subject. T is equals to minus 1 upon k into log e into this value. If we apply this 1 upon k log e with both this term and will open the bracket, it will be minus 1 upon k log e into log F minus Fc minus plus 1 upon k into log e base 10 into this log value. So if we compare this equation with the equation is equals to y is equal to mx plus c, okay, we will get the value of y, that is t, the value of c, that is a constant value, 1 upon k log e into log f0 minus fc. The value of x, which is the variable x and y, this value of x is equals to log f minus fc base 10, and the value of m, which we generally consider as the slope, that the value of slope m is equals to minus 1 upon k log e. So to find out the value of this slope, we would have a graph, and from this graph we can find out the value of slope. Okay, let's clear this thing with one example. Well, the example is the infiltration capacity of an area of different intervals of time are indicated in this table. We have to find an equation for the infiltration capacity in the exponential form, that is the form of E. Okay, here we have the data, time is in interval, and the infiltration capacity with the time duration. We have to find a perfect equation with the help of this Horton's equation. So this Horton's equation is F is equal to Fc plus F0 minus Fc into e raised to kT. So first of all we need to find out this F0 minus Fc. Well, we have this data, and from this data we have to find F minus Fc. Now in the given data the value of constant is 1 because at the time of 1.75 hours the infiltration capacity was 1, and after the 25 minute again at 2 hour the infiltration capacity would be the same. That means afterwards this capacity is a constant, so that value is Fc. So what we need to do, we have to make F minus Fc. F we have at the time of 0, at the initial time, the F is 11. 11 minus Fc is 1. So 11 minus 1 is equals to 10. Same way, 6 minus 1, 5. 3.7 minus 1, 2.7. 2.4 minus 1, 1.4. 1.7 minus 1.7 and so on. So this is our F minus Fc values. Now that we have to substitute in the equation. Well, next, to measure the slope from the graph. So from the available values, if we plot a graph, we can able to find out the slope, that is about minus 0.9 upon 1. Okay, so with this we have the value as a minus 1 upon 1.11. If we compare this slope value with our slope, that is m is equals to 1 upon k log e, we can able to equate this both the term, that k log e is equals to 1.11. Well, the value of e is equals to 2.718, and if we find out the log 2.718, the value would be 0.4343. So if we simplify the values, the value of k would be 2.56. So the equation for infiltration curve would be F is equals to Fc as 1, F0 minus Fc, that value was 10 as per the table, and the value of the k, that is 2.56. So the final equation of infiltration capacity curve is F is equals to 1 plus 10 into e raised to minus 2.56 t, where the F is in centimeter per hour and t is in hours. Okay, thank you so much students for your kind attention. I hope you understand the topic thoroughly. Thank you so much. We'll see you in the next lecture.